Swayam Prabha. Digital India. Educated India.
Hello, welcome to this session. So, after identifying the basic noise components in the PLL, we need to do the noise analysis to find out how noise from different PLL blocks add to the output noise. Okay. So, for that what we have to do is first identify all the noise sources in the PLL. So far what we have done is we have found out the basic noise sources like resistor and transistors. Now what we are going to do, we are going to find the noise of each block. So PFT is a block, PFT adds a noise. So we find out what is the total noise which the PFD will add, and we will model it with its noise spectral density SN PFT. Let me just write this here, S PFT. N is for noise, but here only noise we are dealing with. So, the noise spectral density for the noise added by the PFT is modeled by SPFT here. Then after the PFT you have charge pump. Okay. So, charge pump adds its own noise, and that noise is noted by the noise power spectral density of the charge pump SCP of F. Then you have loop filter. In loop filter you have resistor and capacitor. Capacitor does not add any noise. The resistor adds noise in with respect to its voltage. So, either you write this as a voltage or you write it as your VNR, that is fine. So, then you have capacitor C1, this does not add any noise. You have capacitor C2, okay, that also does not add any noise, and you have VCO which adds noise at the output, and that noise is the noise of the oscillator, which is defined in terms of phase noise. Let us just find out what is this phase noise, and then you have a divider in the feedback, and divider also there is effective noise of the divider which gets added. So, we identify all these noise sources in the system as divider, and by the way you are feeding from the reference itself may not be that clean, that also adds noise to the input. So, S phi in or reference. Okay. Now, this what I have done is I have just identified all the noise sources in the system. Now, we do one more thing. The thing is that in case of PLL, we are making sure that the output phase is locked with the input phase or reference phase, right. So, the variables which we are looking at other than these voltage or current signals at the input and output of the PLL, the signal the PLL locks such that the phase error is equal to 0, which is like we have seen this multiple times, that phi ref minus phi out by n, that is what the PLL will ensure. We treat the noise which is added by reference or PFT or charge pump, phi out, divider, resistor, these are small perturbations in the steady state of the PLL, which means, let me just write, noise is like a small perturbation in a steady state of PLL. Okay, which implies that we can use a small signal model of PLL for finding output phase noise of, you can say, for noise analysis. So, what we need to find is the few things. So, how this reference noise gets converted to the output noise. Okay. So, before we look at that, I will identify that at each point whatever variable you had before, what we have done is we have added the noise within that particular variable only. Example. So, the charge pump output is a current. Okay. So, the charge pump noise is also taken in the form of current only. So, I will call this as ICPN. So, current at the output of the charge pump, the noise is added in current domain. At the output of the PFD, the noise is added in voltage domain which you have, the way we have noted it. At the reference, the noise is added, at the input, the noise is added in phase domain, because what we are doing is the phase frequency detector is finding the phase error. Okay. So, if you just look at the small signal model of this PLL, so PFD, what the PFD is doing, it is finding the phase error between the input and the feedback, and that is multiplied by KPD, which is the gain, right. So, when you are subtracting the reference with the feedback, it is in phase domain. So, the noise which is added by the reference which we should know, that is in phase domain. Okay. So, here this is phase error. This phase error gets converted from phase to voltage by using KPD, right. So, in using this KPD, the PFD acts in voltage domain. Okay. At the charge pump output, it acts in current domain. This is we control. So, your voltage noise here adds to the output noise, control voltage noise in voltage domain. The output phase, we are looking at the output phase. So, the noise from the VCO adds to the output phase in phase domain. So, and at the divider, the noise, the output of the divider is taken as phi divided, right. So, the noise from the divider acts in the phase domain. So, important part here is that your reference noise, we have to find this also independently, that how much noise the input adds independently, PFD adds independently, and those noise sources we have to add here. So, reference noise is in phase domain, okay. Charge pump noise, that is in current domain, okay. Resistor noise, that is in voltage, because it somehow it adds at the node where it changes the voltage. You can use current also, but finally you have to look at the control voltage. And VCO's noise is in phase domain, okay, and your divider noise is in phase domain. Right. So, we found all these noise sources. Now, after finding all these noise sources, what we need to do is we need to find how these noise sources get converted to the output phase noise by the small signal analysis. So, to do that, I will replace these blocks with their linear model. This is a small signal model, which is ICP here, and this is KVCO over S. KPD of the PFD block is 1 over 2 pi. Okay. So, what we define the term called noise transfer function. Okay. Noise transfer function. So, what is this noise transfer function? Noise transfer function tells us that how the noise from one source get converted to the output. So, this is NTF, noise transfer function. So, let us say we want to find, for simple example, how the reference noise, this particular noise get converted to the output noise. So, NTF reference is, what you need to define here is NTF reference, how the reference noise get added up to the output. So, I need to define with respect the transfer function phi out of S divided by phi reference of S. Okay. Similarly, for the charge pump noise, we need to define NTF Cp. Charge pump adds, this is the charge pump current which is added, noise current which is added here. So, I need to define how phi out of S, how we change the output noise with respect to the charge pump noise. Cp n of S. This is how we define the transfer function. Before we go ahead and define all the transfer function, it will be easy for us if we first define the loop gain and then we work out these transfer function in terms of the loop gain, because all these transfer functions which you are seeing here, all these transfer function are for the same loop, just that the point of addition is different, but the point of observation here is same. So, the loop gain of the PLL loop, which is Lg of S, is, because this is a little bigger. So, I will write it like this, equal to your ICP by 2 pi KVCO over S square C1 plus C2, here 2 pi n is there, times 1 plus SR C1 divided by 1 plus SR C1 C2 by C1 plus C2, which is often written as loop gain of S as ICP by 2 pi n KVCO divided by S square C1 plus C2 times 1 plus S by omega z divided by 1 plus S by omega P3. Okay. And if you just want to recall how we got this, we are looking at the loop gain. So, you can break the loop, find how you get the loop gain multiplication 1 by 2 pi ICP, then ICP goes through this loop filter, because of which you get R C1 C2, that gets multiplied by KVCO, it comes in the feedback and then it gets divided by n. So, the divider plays the role of phase output by n, and that is what you get back. So, this is the loop gain. Now, what I need to find is what is the transfer function for the first one, NTF of reference. So, NTF of reference is, you have a change at the input, which is your reference, and how it comes at the output. That is straightforward, because the change, the reference noise adds at the input. So, the closed loop transfer function is going to be n times loop gain of S divided by 1 plus loop gain of S. Okay. In general, you know that for given control loop, let me just define that. For a block diagram like this, if you have a forward path G of S and you have a feedback path, negative feedback path with H of S, right, then the input to output transfer function y by x is given as Gs, that is 1 over H of S times Gs Hs divide by 1 plus GS HS, okay, which you can think about as this is nothing but 1 over HS times loop gain by 1 plus loop gain of the loop, or sometimes you also write it is about the forward path gain divided by the loop gain 1 plus loop gain. Okay. So, this is how it is defined. We are going to use the same thing time and again here. Now, you get ICP. So, NTF of charge pump. So, what happens to the charge pump? Charge pump noise adds in the current domain at this node. So, here you can see this is ICP of n. So, ICP of n gets filtered. So, for ICP we are looking at the output ICP of n, the forward path gain includes only this part. Okay. This is one way to define the forward path gain includes only this part, which is KVC over S into the loop filter RC1 in parallel with other things. Or you want to either you can do it this way, or you can also do it that in the that before ICP you have an extra factor of ICP by 2 pi. That is the only extra factor, right. So, if from the loop gain, if from the forward path gain you remove that, then you will get the same as the same transfer function as you get for the reference. Okay. So, I will write that you are going to have 2 pi, you divide the gain 2 pi by ICP times n times loop gain of S divided by 1 plus loop gain of S. How did I get it? Well, noise transfer function for the reference is this. I should just divide the noise transfer function for the reference by the gain of the charge pump. So, I hope that makes sense. Now, or if you want to do it directly, well, you can do it brute force also, that NTF of charge pump is forward path gain, which is your R parallel 1 over SC1 series in parallel with 1 over SC2 times KVCO over S. This is forward path gain divided by 1 plus loop gain. So, you have this thing in parallel. So, you can write this as 1 plus SR C1 divided by SC1 into 1 by SC2 whole divided by 1 plus SR C1 by SC1 plus 1 over SC2, right. This into KVCO over S into 1 by 1 plus loop gain. Now, this particular factor you have seen it before, I will just cancel S here. So, what you get here is 1 plus SR C1, 1 plus SR C1 from here divided by S C1 C2, and this is going to be C2 plus SR C1 C2 plus C1, okay, whole divided by C1 C2 times KVCO over S into 1 by 1 plus loop gain. So, what do you see here right now? You see that NTF of charge pump is equal to KVCO by S, okay, KVCO by S 1 plus SR C1 divided by 1 plus SR C1 C2 divided by C1 plus C2. Okay. You see here that this is this particular C1 C2 will cancel from both the numerator and the denominator. C1 plus C2 I take outside. So, what you are going to have is C1 plus C2 here, and this is S square, okay, times 1 by 1 plus loop gain. Now, this particular term, what is missing from this particular part? Well, what is missing is only ICP by 2 pi times n. So, I am going to multiply and divide, and 2 pi n divided by ICP. Now, this becomes your loop gain. So, what I see here is you take n from here. So, n times loop gain by 1 plus loop gain into 2 pi by ICP. This is what we directly wrote previously. Okay. So, you see NTF of charge pump. Now, the other one is NTF of PFD. Well, NTF of PFD will have the same transfer function like charge pump. So, I will write that also. NTF noise transfer function for PFD noise is your n times loop gain by 1 plus loop gain, and you divide it by the gain of the PFD, which is 2 pi. NTF of your divider, which is also coming at the same point, which is at the input, right, the input noise. So, this is also going to be the same as NTF reference, which is n times loop gain by 1 plus loop gain. Let me write this, that NTF of PFD, what we are looking at is phi out divided by the PFD noise which you are adding. Okay. So, you are adding this particular voltage noise VPFD. Okay. Then you have for the current noise, similarly we were looking at I think we have talked about it, yeah, phi out by ICP n. Then you get the resistance noise. So, what we need to find is NTF of R. This will be defined by phi out divided by your Vn R, the transfer function which we, the voltage noise which we are having, VNR. Okay. Now, if you look at this resistance, this is little cumbersome in the calculation. So, you have VNR here, which is C1 like this R and then C2. Okay. So, what we do here is we find out that how VNR is first changing the control voltage. Okay. So, to do that, we know that V control of S divided by VNR of S is nothing but 1 over SC2 divided by 1 over SC2 plus 1 over SC1 plus R. Okay. So, V control by S divided by VNR of S is 1 over SC2 divided by 1 over SC2 plus 1 over SC1 plus R, which you can calculate now. This is going to be your 1 over SC2 whole divided by C1 plus C2 plus SR C1 C2 whole divided by SC1 C2. So, V control of S divided by VNR of S, this is equal to, you will remove this S C2 will get cancelled, you get C1 divided by C1 plus C2 plus SR C1 C2. So, if we put in perspective like this, C1 plus C2, C1 divided by C1 plus C2, 1 plus SR C1 C2 by C1 plus C2. So, from VNR to V control we get this. Then what we need to do is we need to find from V control how do we get phi out. Okay. NTF of R I am finding in two steps. One, I need to find phi out by VNR. I am finding out like this, phi out by V control of S into V control of S by VNR. So, the second term we just found, and the first term phi out by V control of S is going to be KVCO by S divided by, this is the forward path gain, by 1 plus loop gain, into the other terms which we are getting from here is C1 by C1 plus C2, C1 plus C2 into 1 by 1 plus SR C1 C2 by C1 plus C2. Okay. So, I can just write it like this, that what we have here is C 1 by C 1 plus C 2 into 1 plus S by omega P 3, which we have been using, K V C O over S into 1 by 1 plus loop gain. Okay. That is NTF of resistor. Now, NTF of VCO noise, what we need to find is how the output noise change in the closed loop with respect to phi VCO. And where are we adding phi VCO? We are adding phi VCO here. Okay. So, phi VCO is added here. The forward path gain is only 1, because you are looking at this forward path gain is 1, but there is a whole loop behind it, right. So, phi out by phi VCO is 1 divided by 1 plus loop gain. Okay. So, what we have done so far is we have found the noise transfer function for each noise source from input to the noise input to its output. Okay. Now, let us have a guess about what these noise transfer functions will look like. So, I will just because we have calculated at many different places, what I will do is I will just summarize at one place. NTF R of S is C 1 by C 1 plus C 2 K V C O by S into 1 plus S by omega P 3 times 1 by 1 plus loop gain. Then you have NTF of charge pump, which is 2 pi by ICP times n times loop gain by 1 plus loop gain. NTF of divider, NTF of your reference, they are the same, okay, which is n times loop gain by 1 plus loop gain, and NTF of PFD only has 2 pi factor. Now, to make sense from these transfer function, the important part which we understand is this loop gain parameter. Okay. So, the loop gain, we have seen that also, it is having like 2 poles at 0, and then it has your 1 pole at omega p 3. So, what we have is something like this, ICP by 2 pi KVCO SU by 2 pi n into S square C 1 plus C 2 and 1 plus S pi omega z divided by S pi omega p 3. Okay. So, for this, if we are looking at the loop gain transfer function, or let us say phi reference, NTF reference. NTF reference is n times loop gain by 1 plus loop gain. You can very well plot it and understand, but you should understand even after by looking at the expression, is n divided by 1 plus 1 by loop gain. Loop gain is given to you here. So, what you see here is as S tends to 0 in this case, right, as S tends to 0, loop gain tends to infinity. This is just hand waving here, that as S tends to 0, right, it implies that loop gain tends to infinity. As loop gain tends to infinity, NTF reference tends to n. And on the opposite case, what you see here is as S tends to infinity at very high frequency, as S tends to infinity, your loop gain tends to 0, loop gain tends to 0, your 1 by loop gain will tend to infinity, and your NTF reference will actually go to 0. So, what we expect here is that the NTF of reference will look something like this. Okay. Then for all other this it should appear like this. Okay. Then if you look at the transfer function NTF of VCO, NTF of VCO is 1 by 1 plus loop gain. NTF of VCO is 1 by 1 plus loop gain, right. So, as S tends to 0, loop gain tends to infinity. As loop gain tends to infinity, NTF of VCO will tend to 0. So, what you will find is that NTF of the VCO will look like this apparently. Okay. Then NTF of resistor. In NTF of resistor, you are having 1 by 1 plus loop gain, so it is like this transfer function getting multiplied by a low pass transfer function which is KVCO by S divided by 1 plus S pi omega p 3. Okay. That is what you have here. So, if that is the case, your high pass transfer function is getting multiplied by low pass transfer function, which is a low pass transfer function is like maybe depends on where the poles and zeros are, maybe something like this. So, overall what you may find for your resistor transfer function, that may something look like a band pass transfer function, because at high frequency your NTF reference is going to take it, your low pass transfer function effect which is S square, that is going to take it down. So, this may be NTF of R, and then NTF of charge pump, that is only a gain factor here. NTF of divider and reference are the same, NTF of PFD is only a gain factor. Okay. So, let me just plot all these transfer function for one particular example, okay, after choosing certain numbers and show it to you. Okay. So, you see this plot. In this case, NTF of reference is this blue one, it is plotted like this and it is a low pass. Here I am choosing my reference frequency as 40 megahertz, okay, and my plot is only till f ref by 2. If you recall our discussion in the previous session, our continuous time or S domain analysis, the way we are doing is valid only for frequency contents which are for bandwidth which are lesser than f ref by 10, and it is a sample system, sample at f ref. So, we are showing only the plots till f ref by 2. Okay. So, till f ref by 2, what you see here is it is a low pass transfer function. Similarly, you look at NTF of VCO. So, NTF of VCO is this. So, for this NTF of VCO, what you see here is this is a high pass transfer, it increases and then it becomes flat. Okay. NTF of resistance. So, NTF of resistance we were looking at that it should be a kind of a band pass transfer function. It depends on that which has a higher order. So, let us look at it. This term is having a second order, whereas loop gain term is having a third order, right. So, what is going to happen here is that in loop gain, as you see, it is a third order system at S equal to this is a second order at S equal to 0, that is loop gain close to S equal to 0, whereas this particular at S equal to 0 you are only going to get an order from the other term. So, this is going to dominate. So, in place of red curve which is starting from here, it may start from here. Okay. So, that is what you see for the NTF of resistance. NTF of charge pump, it is a low pass transfer function just multiplied by gain. So, without even plotting it, just looking at the expression, you can make out that which is going to be a high pass, which is going to be a low pass and other stuff. Okay. So, what you can conclude from here is that all these noise sources are getting filtered by different noise transfer functions. When different blocks are getting different noise sources are getting filtered by different noise transfer function, what we need to do is we need to find the output noise. So, the output noise S out due to the reference noise is going to be your noise spectral density of the reference noise source, which was S ref in our example. Let us just look at it, S phi ref okay, S phi ref, this was the noise source which we have, and this gets multiplied by the noise transfer function of the reference. So, this was the noise power spectral density. Noise transfer function was in your not in the power domain, it is like either voltage to voltage, phase to phase, or current to voltage. So, when you are multiplying these transfer functions, this will be square here. Okay. So, the noise power spectral density gets multiplied by the noise transfer function to give you the output noise due to reference. Similarly, the noise at the output due to charge pump is your charge pump noise multiplied by the noise transfer function for charge pump. The resistance noise at the output due to resistance is going to be the noise power spectral density due to resistor, which we have been writing as VNR or VNR itself, right. So, SR into NTF of R whole square. S out due to VCO, that is VCO phase noise, is your S phi out, the VCO phase noise. Let us write this as phi VCO times NTF of VCO whole square. So, what we have done is we found the noise sources, we found the noise transfer function for each of these sources, and after finding the noise transfer function, we calculated the noise at the output due to different noise sources. Similarly, you will have for the divider S divider times NTF divider. Once we, and all these S is actually all these are output noise power spectral density due to different sources. So, to calculate the total noise S out total, all these noise sources are independent of each other, they will add up, their noise spectral densities are going to add up plus S out charge pump plus S out R plus S out of VCO plus S out divider plus S out PFT. So, we can get the final output noise power spectral density due to different noise sources, due to the noise contribution from different blocks, and we can find the total output noise spectral density. Let me show you one of the simulations which we have done to find the total output noise. So, here we found the noise spectral density, it actually depends on what whether the noise is flat, input noise is flat or not. So, let us look at the resistor one first. So, we know that the resistance noise is 4 kTr, which is flat, right, and the noise transfer function is band pass in nature, that is what you see, the output phi out because of resistor, right. I have been writing out here, but all these are phi outs, because our measurement is in phase domain. Okay, that does not make any difference here. So, this is your output noise. Now, you look at the reference noise. Reference noise, depending on what noise we have, the reference noise will also be low pass. If it is flat, charge pump noise, the current noise is normally flat, as we have talked about. So, charge pump, though we have not talked specifically about the charge pump noise, but the current element which you have there, that noise is flat, and it turns out the charge pump noise spectral density is also flat. So, the output noise spectral density of the charge pump is also low pass. Then you get the VCO. VCO is a little tricky part, and what happens is that the VCO phase noise is not white or not flat, it has some transfer functions. Well, whatever that noise we have, we multiplied that noise with the noise transfer function, and it turns out that this noise appears to be a band pass characteristic here. And then we add up all these noise sources, whichever you are seeing, and the final resultant noise is shown to you in terms of let me just erase this part, so that it becomes little clear. So, the final output noise, you add all these terms and the final output noise is this. When you have the final output noise power spectral density for the phase, what do we have effectively? We have the noise power spectral density, noise power spectral density for phi out, right. This is power spectral density. So, the total noise power for the phase error, or because this is whatever we are calculating is due to noise. So, that is like the disturbance in the output phase. So, we can find the phi out mean square value of output phase error by integrating this total output noise as total phi out with respect to frequency. We will get the mean square value of the. So, we know that the power in the area under the plot in the frequency domain will give us the power for the signal in time domain. So, we get this phi out, and how jitter is related to phi out? Well, delta t is 2 pi times, sorry, delta phi or the phase error is related to 2 pi times delta t by t. So, the jitter time in time domain, jitter value sigma, okay, is defined as t by 2 pi, you just need to use this expression, is square root of s phi out total df, and you will get the jitter in seconds. Okay. So, now you see that based on the loop gain transfer function, your noise transfer function depend, and depending on the noise transfer function and your input noise for different blocks, you get the total output noise, which will finally lead to jitter. If you vary your bandwidth, you vary the noise transfer function, this jitter will vary. Okay. The next thing which we need to look at is that how this jitter varies with bandwidth, how different noise sources. Right now, we have said the fundamental element is resistor or transistor, how noise from different blocks like PFT, charge pump, VCO, that translates to the output phase noise. Okay. And once we know that, then we need to find that, okay, we have this noise, then how to choose an optimum bandwidth and look at the trade offs. Okay. Thank you.